If you're building electric circuits, you know that the circuit itself is only half the story. The other half? Figuring out how to power the thing. So today, we're going to get right to the heart of any portable device, its power source. You see this number every single day, right? But what is that 100% actually telling you in electrical terms? To figure that out, we have to dig into what a battery is and how we measure its capacity. All right, first things first. Every single circuit needs a source of direct current, or DC voltage. You can think of it as the engine. It's what provides that constant push to get electrons moving and make your designs, well, do something. Now, these DC sources usually come in two main flavors. You've got your power supplies, the benchtop ones you use in the lab. They take the AC power from the wall and turn it into the nice, stable DC voltage you need. And then, of course, there are the portable powerhouses we can't live without, batteries. So how in the world does a battery actually work? Well, it's not magic. It's all about chemistry. And here's a really common misconception I want to clear up. Batteries don't store electrical charge. Nope, what they store is way cooler. And this is the absolute key. A battery isn't like a capacitor that just holds onto electrons. Instead, it's packed with chemical potential energy just waiting for you to complete a circuit. The moment you do, a chemical reaction kicks off and it converts that stored energy into a flow of electrons, which is your electric current. This classic copper-zinc cell shows the basic idea perfectly. You've got two different metals, the electrodes, and they're sitting in these solutions called electrolytes. A chemical reaction is just dying to happen, but it can't. Not until you give the electrons an external path to travel on. And guess what? That path is your circuit. The engine driving this whole process is a special kind of reaction called an oxidation-reduction, or just redox reaction for short. To put it simply, one chemical is giving up electrons while another one is ready to accept them. By keeping these two chemicals apart inside the battery, we force those electrons to travel through our circuit to get from one to the other. And boom, that's your current. Okay, so we know the energy comes from a chemical reaction, but how do we measure how much energy is in there? How do we quantify that 100% we see on our phone screen? Well, this brings us to one of the most important specs for any battery. The spec you've got to know is the ampere-hour rating, usually written as AH. And it's pretty much exactly what it sounds like. It tells you how many amps of current a battery can supply, multiplied by the time and hours it can keep that up. It's a direct measure of the battery's total capacity. A really good way to think about this is with a water analogy. Imagine voltage is the water pressure, and current is how fast the water is flowing out of the pipe. Well, the ampere-hour rating, that's the total size of the water tank. It's how much water you have to work with in the first place. So for instance, let's grab a common 12-volt battery. You might look at the side and see this rating, 6.5 ampere hours. This isn't just some abstract number, it's a real-world spec you'll see on components you actually buy for your projects. Okay, that's the spec, but how do we use it? This is where the theory gets super practical, and honestly, pretty essential for designing anything that isn't plugged into a wall. The most direct and powerful thing you can do with the A-hour rating is estimate how long your project is actually going to run before the battery is toast. This is a must-do calculation for any kind of portable design. And the calculation is beautifully simple. Step 1, look at the battery, find that AH rating. Step 2, figure out how much current your circuit is going to pull. You can measure this or calculate it. Step 3, just divide the AH rating by the current draw. That's it. That gives you the estimated life in hours. So let's run the numbers with our 6.5 hours battery. Let's say we hook it up to a circuit that's constantly drawing half an amp, or 500 milliamps. The math is simple. 6.5 ampere hours divided by 0.5 amps, and that gives us an expected runtime of 13 hours. Now, here's the catch. And for any of you going into engineering, this is a big one. That calculation gives us a perfect, ideal number. But as we all know, the real world is messy. It's a little more complex, and a few key things can change that 13-hour estimate. That ampere-hour rating on the label, it's a fantastic guideline, but it's not the whole story. Things like temperature can really mess with the battery's internal chemistry. If it's too hot or too cold, you're not going to get that full capacity. Also, how deeply you discharge the battery and how fast you pull the current out can affect its performance and its overall lifespan. So, the takeaway here is to treat that calculated number as a really solid starting point. It's a great first estimate to get you in the ballpark, but you should always, always test your circuit under real-world conditions to see how it truly behaves. But at the end of the day, understanding this one rating is incredibly powerful.
It lets you make smart, informed decisions when you're choosing the right battery and trying to predict how your circuit is going to perform out in the wild.
And that leaves us with a final question to chew on. We all want our devices to do more and last longer. So where's the next big breakthrough going to come from? Is it going to be from chemists creating incredible new batteries with way more energy density? Or is it up to electrical engineers, like you, to design smarter, more efficient circuits that can do more with less power? It's something to think about.